Morning, Hannah. Oh, perfect. You're first in the alphabet, and you're the first one here. Okay. Well, that didn't last long. I was just saying it's perfect because Hannah's first in the alphabet and first one here. Then you had to show up early and throw everything off. Right. So one's not much of a pattern anyway, so.
There have been two though.
Thanks for phrasing this. It's a good thing you showed up when you did. It's unlikely the pattern would have held up anyway.
I'm not gonna lie, when I woke up this morning and I didn't see any snow, I was a little sad.
You were happy or sad?
Sad.
Yeah. I don't know, man, I got an extra 15 minutes of sleep because I didn't have to go clear the driveway.
Yeah, that's true.
And actually got here on time. So I feel you, but at the same time, I'm gonna go ahead and disagree with you.
Yeah, I get it.
Can you see that when it's right on the board from the back? That's not too much glare or anything?
Yeah, because it's kind of up and offset,
Okay.
right?
It actually is really handy to be able to do this because it lets me draw right on the slides, which is something I missed about doing digital last year, was being able to do that.
Yeah, Kathy does that a lot.
Yeah. I've had some classrooms where I tried to do that, but there was so much glare that you couldn't see the slides at all. And I don't think it'll translate too well to the recording, but you'll still at least be able to tell vaguely what slide I'm on and see the writing. But I think it'll still work. Guralski?
Good morning.
It'll take a few minutes while everybody's getting here. Check out your test. We'll go over some of the common mistakes, of which there were several.
Dude, I told you I didn't know she was your wife, buddy. Damn that tequila. 55, is that good?
What did you get? 55?
He's got to be netted this week. So.
I did better than I tried. I got 79.
All right, we're in the same boat. We're not answering 2 questions. I couldn't have done better. I mean, I literally, since Reagan didn't help me out with that last question, that's all I got. I just drew arrows up and down and whatever.
You drew more arrows than I did. I drew like the first 3 parts of the reaction, and then I was like, I have no clue what's going on from here.
I mean, he spoon fed us this because he gave us the practice exam. Couldn't have matched this any better than he did.
I did good on the parts that I thought I was going to do good on, and I did bad on the parts that I thought I was going to do bad on. It kind of went exactly how I thought, but I got more points than I thought I was going to get.
Yeah.
And the part where you're supposed to circle the intermediates on the graph, I got wrong because I circled the transition state. And during the test, I was like, I feel that's wrong. I feel like it's the dips, not the humps. But whenever I change something, I usually get it wrong, so I'm not changing it.
You didn't, yeah. It is what it is. The beauty is, unlike Richardson class, where I didn't score so well at his midterm, and that's going to be hard to compensate and backpedal and make up for. At least here, we can make up in quizzes and homework.
Mm-hmm.
So there's like, the tests are not a huge part of the grade, where 80.
I was way less stressed about it. And I feel like tests should not be a huge part of the grade. Tests should be to see what you're understanding and what you're not understanding.
87.5% is Richardson's weight on the 2 or the 3 tests that we take, which is huge, right? Yeah.
All right, we'll go ahead and get started here. So I had forgotten until yesterday at about 1 o'clock in the afternoon, I forgot about Veterans Day on Thursday, which will mean we will not have lecture on Thursday. Celebrate those veterans, and we'll pick back up next week. But it just threw off my lab schedule for Gen Camp, because instead of Wednesday, Thursday being the lab this week, it has to be Tuesday, Wednesday being the lab this week. So, and I don't have much time to prep in between this lecture and the start of lab 10 minutes later.
I secretly celebrate Veterans Day because 2 years ago, that's why I moved my mother-in-law out of the house. Veterans Day.
Veterans Day, there you go, 11/11.
That's a beautiful day.
Anybody know where 11/11 comes from?
World War I ended on the 11th hour of the 11th day of the 11th month.
Very good, Treaty of Versailles.
Wow. So my first one was almost 2011. The water broke, we went in, actually it didn't break, it was Braxton Hicks
Oh, okay.
infections, and they sent us back, so 11/17/11 was my first one.
The water just ruptured.
The water never actually broke, they did nothing, had to poke that thing to get it to, just that other stuff going on.
Childbirth is a thing. It's a hell of an operation.
Yeah.
All right, so everybody did well on the first page. Most people did well on number 2 as well. The most common mistake was by forgetting a hydrogen. Everybody forgot that there was a hydrogen on that one single sp3 carbon had an extra hydrogen on it. Not everybody forgot that. A couple people. Cody.
Thanks, Brad.
No problem. And so, yeah, when I say things like everybody or a few people in this class, with only 7 people taking the test, that, it's a very small sample size. I'm not even going to show you the statistics for the test because it doesn't matter with only 7 people.
Yeah.
The other thing that people missed on page 2 was how many lone pairs can participate in resonance.
Yeah.
A few people forgot the chlorines had lone pairs, and that the lone pairs were conjugated on the chlorine. So the chlorines lone pairs could participate in resonance, and one of the nitrogens had a lone pair. The bottom nitrogen had a lone pair that could participate. So I'm going to pull up the test so that we can gesture and show you what I'm talking about on some of these. So there were three lone pairs that could participate, because remember that the oxygen that's in the form of an OH has lone pairs and doesn't have any pi bonds already participating, but it has an sp3 carbon blocking the way. And sp3 carbons that's a hard no when it comes to resonance, because there's nothing you can do when they already have 8 electrons that are all sigma bonds. And so this nitrogen's lone pair could participate in resonance, and the 2 chlorines each had a single lone pair that could participate in resonance.
Hello. Thank you.
Welcome. Resonance structures, so you guys struggled a bit collectively. The main thing, so there were a couple of oxygens that had 10 electrons around them on this first one. There were a couple, that was the most common thing, and then trying to move too many pairs of electrons at the same time. Remember, all you have to do to draw the next resonance structure is just draw 1 pair of electrons moving at a time. So the first thing you could do, you move those over, and then you get everything stays where it is, except you took electrons away from that carbon, so the positive charge is there. So you get that. Then you can move it over. So that's moving those electrons over. And then the last one was you can move lone pair from the oxygen over this direction. You can't move, there's no way to move the lone pair of the oxygen over to this carbon, because there's never a vacancy on this carbon. Right, this carbon always has a pi bond on it at all times. So there's no way for the oxygen to resonate towards the right, it can only resonate towards the left carbon. And so then our last one, resonance structure looked like this. And then ranking them, so we have 4 options, right? 1, 2, and 3 all have a carbocation. It's a secondary carbocation for all of them. So they're all going to be relatively the same level of stability. So all 3 of these are a distant number 2 to this one. This is the only resonance structure where everything has a full valence. Right, so that's what I was looking for mostly, was you recognizing this one was going to be, I'll get that later. It was a blind shot. What I was most looking for was you guys realizing this one was going to be the number 1 resonance structure, because everything has a full valence. Brad?
Does the oxygen still have full valence?
The oxygen does still have a full valence, because you didn't full on take any electrons away from it, you just made it make 1 extra bond. Because if we look at all of the electrons on this here, and let me blow it up over here so we can look at that one specifically, since it got a little crowded over there. You still have 1 lone pair on the oxygen. And
So now it's a partial.
right, so it has a positive charge. It has a formal charge of +1, because it's got 3 bonds, and oxygen normally wants to make 2 bonds. So we're making it share more than it normally does, but it still has a full valence. And that was the key to recognize, is that formal charge a formal charge of 1 on an oxygen, a +1 on an oxygen, can still be better if it means we get to fill all the valences. And again, we went over this, it's been a while since we went over these, and we didn't do a whole lot of review because I ran out of time to give you guys much review with me. You guys did all your review with Carl, and then we're so preoccupied with the mechanisms, which I was actually very pleased with how number 9 went. You guys can recognize mechanism steps pretty well, although drawing the mechanism steps will still need some work on, but we'll get there. Part of that's probably just because I made it number 10, so you guys ran out of time.
Do you mind if I take a step back real quick?
Yeah, go for it.
I'm just curious, I think you already demonstrated it. How does the lone pair and the chlorine resonate? Do you have any?
So remember that the chlorine's got 3 lone pairs, and it doesn't have any electrons in a pi bond yet. And so it's got lone pairs that are adjacent to a pi bond, which is a clue that it can resonate. And so what it would look like would be something like one of these lone pairs moves over, and this pi bond sort of breaks and moves the negative charge over. So we would get a resonance structure that looks like, I'm just going to draw the benzene, not the whole molecule. Get something that looks like this. Right, so, and again, we didn't break up any full valences to do that because having a negative charge on a carbon still means the carbon has 8 electrons. And the chlorine still has 8 electrons around it, it's just making 2 bonds instead of 1. So this is actually a relatively significant resonance structure. It will donate electron density to that benzene ring by basically letting its lone pairs sort of spread out. And that is a particularly tricky resonance structure to draw, which is why I didn't ask you to do any of those on the next page. This bottom one, I think, had a total of 5, if I'm remembering properly, but most of them look pretty much the same as what you have here. That one of the tricks was recognizing, okay, well, if I've got a lone pair here adjacent to a pi bond, that's one of those patterns where we are always going to have resonance together, an allylic pi bond. Right, on an atom adjacent to a pi bond, we have a lone pair. Right, so the first resonance structure would look something like lone pair moves down, and then we have to move this pi bond over to make room for it. So you would get something that looks like this. I'm just leaving off the hydrogens. And then you can have another one where the negative charge is over here, where you move these electrons this direction to make another pi bond, which pushes the negative charge here. And then the last one is one where you put, and remember with these arrows, we're always drawing where the electrons are moving. So I'm going to jump all the way to the furthest resonance structure, so 3 arrows at once. You got a negative charge on the oxygen, pi bond, pi bond. And if we're ranking these in terms of stability, the most stable is one with no formal charges. Everything's got a full valence and no formal charges. So this is best, followed by this one because it puts your negative charge on an oxygen and furthest away physically from the positive charge. And then all the ones in between are going to be roughly the same level of stability. Again, I try not to be, I also want to say something about the grades, just because if you're in this class, it's because for the most part you did well in Gen Chem and you're used to getting pretty good grades on tests. this is a second year class, which means grades, you're going to feel, it's going to feel like it's harder in terms of the grades, just because you're now competing against only a room full of people that are also good at chemistry. So I'm not trying to ramp up the competitive atmosphere or anything like that, just helping you recognize that this is going to be a harder class to get an A in, just sheerly by who's in the class and the fact that we're dealing with second year material. That said, you know, this class is still set up so that everybody, I can have a class average of 80 on the test, and everybody can still get A's if you do well on the quizzes and and get all your assignments turned in. So nobody is in a position where you should really be that worried. And if you did worse than you wanted to on this first test, well, that's actually not all bad, because now all you have to do to raise your grade in the class is do better than you did on this one on the next test. Right, so if you bombed this one, if you got a 70 on this one, and that's bombing for you, and you're sitting at like an 88% in the class now, that's okay, because if you can go from 70, if you can get 85 on the final, now that you know how OChem tests work, then all of a sudden your score can jump a lot just by getting the class average on the next test. Right, so it's not all bad to have, you're sort of setting yourself up for improvement if you did worse than you wanted on this first test. And if you did worse than you wanted on this first test, but you still have an A in the class, good news, because all you have to do to keep that A is do the same on the next test. All right, so don't panic or anything. Nobody has got a grade where you should be panicked about this. Nomenclature, you guys for the most part did well on this. Those parentheses are hard, and I gave you 3 out of the 4 problems had the parentheses, right? So if you struggled using the parentheses with these complicated branches, then you didn't do all that great necessarily. You didn't get a 10 out of 10 anyway. But I think there was, only one kind of 10 out of 10 anyway on this section. So we will keep practicing with those. Was there anything in particular anybody wanted to see? I also have the key up here too that you guys can take a look at. It's a little messy because I don't usually give out the key. It's for my own reference, but you're willing to check it out during lab or after class as well, or during break if you want to check your answers compared to mine.
Yeah, can we do the first one?
Yeah. So this one, when I look at this, the easiest way I can see along the chain is there's 7 in a row right there. And you can't get 7 in a row any different way, really. You could call that carbon 1, but then you still have a methyl on carbon 2. It doesn't really change any of the branches, right? So to start with calling that heptane, you've got 2 methyl groups on carbon 2 and carbon 6. Or you could count 2 and 6 from the other direction, you get the same numbers. So 2,6-dimethyl. And then on carbon 4, you have a complicated branch, so we're going to do it in parentheses. It's a ethyl group that has a methyl attached to it. So ethyl goes second because this is the longest continuous part of the branch when you start counting. And remember, with these branches, carbon 1 on the branch is always whatever's directly attached to your parent group. Right, so that's not carbon 1 on your branch. So it's an ethyl group that has a methyl attached. So methyl, ethyl, in parentheses. The parentheses are telling us that this methyl branch that we're talking about is attached to the ethyl. We don't really need a number in front of the methyl because there's only one place you could attach a methyl group on an ethyl group. So this is what we were looking for. You could call it an isopropyl group, but again, to me, it's more worth to remember all those various common terms for some of these more complicated branches than it is to just learn how to use the parentheses, so I'm going to keep emphasizing that. You could call it an isopropyl group. On number 2 here, you've got a branch that is 3 carbons long that has a methyl attached to it. So I'm just going to go through and look at the complicated branch here, because I think we can all recognize that cyclohexane, right? And number-wise, if we call that 1, that's 4. And we need to remember that it was cis, meaning that they're on the same side of the ring, meaning they're both sticking up above the ring. When we talk about on the same side for cis, we mean relative to the plane of the ring. Are they both above it or both below the plane of the ring? That would be cis. If it's on opposite sides of the plane of the ring, that would be trans. So this one, the parentheses for this one is it's going to be a propyl group that has a methyl attached to it. So it's a methyl propyl group. But with a methyl propyl, there are 2 places we could put that methyl. Right, we could put it here or we could put it there and still have it be a propyl group. So we need to specify that it's on carbon 2 of the propyl group. So inside the parentheses would be a 2-methyl propyl group. Right, so the key is that common mistakes with the parentheses were either mixing up the order here or messing up your numbers because you started by counting this as carbon 1 instead of that as carbon 1 for the branch. Yeah, it's just something that takes a little bit of practice. When you get it down, it becomes second nature. When you open the parentheses, we're now talking about a whole different world than the rest of the molecule. And so, but all of our same rules still apply. If you wanted to use the common names for that one, I believe that's an isobutyl group. But only one person used common names. And she did so properly, so I'll allow it. As opposed to 1-methylpropyl, a 1-methylpropyl group means that when we're comparing to the rest of the molecule, it's just cyclopentane, we can draw it real quick. Inside the parentheses, our 1 branch is a complicated branch. We have a propyl group, so start by drawing 3. 1, 2, 3 carbons. And it has a methyl on the propyl group on carbon 1 of the propyl group. So it looks like that. And if I was not paying attention, I was specifically not looking to test you on R versus S to this point, but there is an asymmetric carbon on that molecule. Where is it?
It's a 1-methyl.
It'd be the 1-methyl. This carbon right here has 4 different things attached to it. So this would be something that I did not give you enough information to say whether I wanted you to draw the R or the S, so just draw it like this. If I said R, you would actually have to go in there and look at the 4 things that were attached to the carbon and figure out which way to draw it.
Thank you.
A little bit of take-home situation.
So assigning priority for something already drawn is where you usually learn it, but it's actually not that much harder to draw a specific stereochemistry because you just pick one and draw it. And then, so let's say if I was looking for R, just pick one and draw it. Let's just say, okay, I'm going to draw the methyl sticking out towards us. And then you figure out whether you just drew the R or the S. And if you drew the S, you just switch it. You just swap any 2 of the substituents. Usually the easiest thing to do would be to take this one sticking up and make it sticking into the board. So that's the best way to make sure that you get the right stereoisomer when I give you a specific stereoisomer to draw. Is pick one. You got a 50-50 shot of getting it right. And if you mess it up, just switch any 2 of the substituents and you switch to the other isomer. Right, so it wouldn't have been the end of the world, although without me telling you that trick, it might have felt like it, especially in that time test. And then everybody got this one right, which tells me that it really was the parentheses that throw you off the most. Nobody got a 10 out of 10. Maybe one or two people got a 10 out of 10 on the nomenclature page, but everybody got that one right. So that tells me something, right? All right, so in general, you all did pretty well on this one too. So I'm not going to spend a lot of time here, other than to say, I think the only repeated mistake, the only mistake that happened more than once was people forgot how many methyls were going to be on that second carbon. So when you do one of these, the first thing you might want to do is draw the skeletal structure, so that you make sure you're not missing a carbon when you do your Newman projection. So with 1 bromo, 2-methyl propane, well, there's propane, 1 bromo, 2-methyl. And we're supposed to look that direction. So you had 2 CH3s attached to the back carbon in your Newman projection. But a lot of people missed that second CH3. All right, so, and then, so our front carbon can look something like this, with 2 hydrogens attached. Our back carbon would look in the lowest energy conformer, with something like this. You basically are stuck with one of the methyls has to be gauche, but the other one can be anti. We want anything to be anti, right, as much as we can, keep our big groups away from each other. But you only have 3 places to put 2 methyl groups, so one of them is going to have to be a gauche. The other thing to remember is that lowest energy means most stable. There's 1 or 2 or 3 people who flipped that, and for this top part gave me the least stable, the highest energy, and then switched it and gave me the correct low energy isomer down below, or complement rather.
So I just want to be clear, highest and lowest energy doesn't mean highest or lowest stability, correct?
Correct, they're opposite. Low energy is more stable. Right? And then for the highest energy conformer, you were looking for a potential energy minimum, a local minimum, then you would have been looking at having both of these gauche. So something looked like CH3 here and CH3 here. So you put all of your big groups on the same side next to each other, or if you made it as a transition state, would have been when you actually have it fully eclipsed. And remember I told you that, so this is technically the highest energy conformer, because technically the transition state, when you're rotating these things by each other, the transition state being at the top of the potential energy surface, it's not really a conformer by our true definition, but for now, it's the highest energy state when it comes to rotating these around. We just wouldn't call it a conformer if we're being really, really picky about our language. But I didn't mark anybody down for that. Right, and that would look like one of these methyls being eclipsed by the bromine, being directly behind it. It doesn't matter which one, it's going to be the same energy either way. The most common mistake on this one is that when you drew this, if you managed to draw it so that both of the substituents were axial or both were equatorial, then you drew the trans conformer, not the cis conformer. Because if it's the cis conformer, or isomer rather, sorry. If it's the cis isomer, then in the chair conformation, it's going to look, we're going to need one thing sticking, if we think about this as being the flat hexagon, looking at it from above, having one sticking straight up like this, and one sticking axial like this would be the cis, right? Because if I took this, remember where the other ones are, the hydrogens, and I'm just trying to not make them not stand out as much. That's the other position on each of those edges, right? And so if I took this picture, if I took this and flattened it out, this is how you get both of these sticking up the way it's drawn here. If you switched them so that your hydrogen was over here and your isopropyl was down, now think about what that looks like if you flatten out that hexagon. Now you have one sticking up and one sticking down. So this is the trans isomer, not the cis isomer. So the cis isomer would look like this. And so our two choices are, we can have a methyl in the axial position and isopropyl in the equatorial, or if we do the chair flip, we wind up with the methyl being equatorial and the isopropyl being axial. So this was a little bit of a curveball because we'd only dealt with things that were the same size on our examples.
Wait, okay, I'm having a hard time. So like when I was thinking about the chair, I was like, it goes axial up, axial down, axial up, axial down, like when you go carbon to carbon.
Mm-hmm.
So how does that, I'm just trying to, like, how does one end up axial and the other equatorial? If looking on that, they look.
Because cis and trans are not the same as saying axial and equatorial.
Okay.
Cis and trans means that if you draw the ring structure flat, that they'll both be on the same side of the ring. Either both be above the ring or both below the ring.
Yeah.
Axial and equatorial, though, just mean, is it pointed towards the rest of the molecule or not?
Okay.
If I took this and I rotated it up so that it was flat, not all the way up there, but so I rotated it like this, the isopropyl would now be up there, right?
Yeah.
And if I did the same thing on this side, if I took this and made it flat, the methyl would go there. Right, and in each of these, the other position is going to be like that, right? So here's our hydrogen, here's our hydrogen.
Yeah.
And you let it go back to being the chair conformation, that puts this one in the equatorial position over here, and this methyl is in the axial position, sticking straight
Okay,
out.
I see. That's tricky.
It is, it's really, really tempting to conflate
Yeah.
cis-trans and axial equatorial, but they're not the same.
Okay.
You know what I hate about being a student?
Using the model was a big help for me.
Is you make it that when you do it, it's like, duh. But when we're doing it, it's just so.
We get that, and that's, you know, especially in a high-stress situation. You're in a hurry, you're trying to go as fast as you can, you put all this pressure on yourself to try and do as good as you can on the test. You're gonna miss stuff like that. That's why tests are not the ideal way of assessing whether or not people really know stuff, necessarily. It just demonstrates whether you can perform under pressure, which is a totally different skill. So, you know, that's why this class is not just midterm and final.
Well, thanks for the points, you know, even though I'm
Yes.
wrong, there's some points for just drawing the stuff, I guess.
There's some points for drawing the stuff, and if you answered correctly from the isomer that you drew, if you drew the trans version instead of the cis version, but then you answered the question correctly, which version is more stable, then you're showing me some knowledge there, even though because I don't want to give you a 0 out of 10 just because you messed up cis versus trans when you drew it. Right? There's a lot more to this question than just draw the conformers. Right? So, you know, I try not to mark you down more than once for the same mistake. Generally, some mistakes are worth more than others, but in general, if you make a mistake at the beginning of the problem, I'll follow your logic the whole way through. So you can still get most of the points if the rest of your logic is sound. Which also, test-taking strategy, at least for my test, but for all tests in general, for multi-part questions, if you don't know how to do part one, give it your best go, and then answer everything else as though you did number one correctly. Right? Because just because of the order that I put the question in, don't let that give you a 0 out of 10 on the whole problem. Right? There's still a lot of points in there and a lot of ways you can show me you understand stuff. And even teachers who are not going to give you any of that other partial credit, they'll still look at it and say, well, they really do understand this stuff. They just messed up on part one. And that goes a long way when it comes time for final grades, when it comes to, well, you're right on the bubble of an A and a B. You get an A or you get a B. You know, a lot of those, you know, when you're in a class of 500, it doesn't matter as much. But little things like that, showing effort, showing that you get most of it, even if you didn't get all of it, goes a long way there. This one was a problem for you guys. Brad,
I think the book lied to me.
you think the book lied to you?
Yes.
Okay, I'm open to hearing this.
The first one anyway. It said, if it's an enantiomer, wedges become dashes, and dashes become wedges. And I used that logic from the book for the first one. Apparently, that is not the case.
Correct, because the book, a lot of people said that because what you were missing is that there's a mirror plane in the middle of this molecule. If you draw a line right there, you got the same molecule on both sides, right? If you have a mirror plane in the middle of the molecule, the mirror image is the same molecule because it's a meso compound. So this was a tricky one. The other way that you can see it is if you picture, and with these ring structures, it's pretty easy to picture them looking like a pancake, right? Picture taking this and flipping it like a pancake and you get that without doing any changing of the mirror plane or any of the stereocenters. The other way you can see this is if you think about trying to assign this carbon right here as being R versus S, it doesn't have 4 unique things attached to it, right? Because going this direction around the ring is going to look identical to going that direction around the ring. And actually, when it comes to our priority, same for any of these carbons. If you try to go this direction around the ring or that direction around the ring, you're going to assign the exact same priority to both sides. So if you can't decide whether that's 2 or 3 or 1 or 2 because it's identical on both sides, it must be because it's not really a stereocenter. It's a stereocenter in that it's cis versus trans, not in terms of R versus S. This one was a little tricky. Definitely not a constitutional isomer. This one was the enantiomer. Right, because if you picture what that molecule looks like flattened out, so the one on the left is going to look something like that. And the one on the right is going to look like that when you flatten these out. And this one doesn't have an internal mirror plane. If you took this and flipped it like a pancake, you get the same molecule back. It doesn't look like that all of a sudden. It's like a right-handed screw versus a left-handed screw. When you take the mirror image of you take a right-handed screw, there's nothing you can do to make it a left-handed screw. Or a fan blade for that matter. Right? And so these were the enantiomers. Almost everybody figured out, I think everybody figured out this was the constitutional isomer because it's the same formula, but instead of having an ethyl group, you had a dimethyl version. Same formula, different branches, tells us it's a constitutional isomer. And then this one, again, I was a little bit tricky with you because I left everything as dashes, but I changed the position of everything else. right? So the book says is if it's an enantiomer, wedges become dashes and dashes become wedges. That's assuming that everything else that's in the plane stays in the same spot.
You're supposed to label your assumptions.
Yes, that is you can blame that partially. Oh man, I got a piece of dry erase marker in my eye. You can definitely blame that book for that one and not making it entirely clear. And I'll just go on record to say there's a reason I didn't present it to you that way. Because that only works if you don't have a meso compound and everything stays in the same spot. Everything else stays where it is. So basically, if it's like a light switch, where everything's in the same spot, and you just click the light switch to go from down to up, that's when you can tell whether or not you inverted it. The one on the left was, I don't remember, was it R or S? Yeah, so the one on the left is S and S. The one on the right is S and R. So one of them got flipped, but not both, so it's a diastereomer.
The first one was what again?
And the first one was the same molecule.
All right, let's retake the test. I'm ready. We'll do the same time.
Same test, same question.
This one was tricky, and I actually made the same mistake that a lot of people made when it came to the one on the left. When it comes to assigning priority, chlorine is going to be number one, so that's the highest atomic number. It's tempting to say this is number two because it's the next biggest thing. It's more complicated looking than the isopropyl group. But when it comes to our tiebreaker, it's however you can break the tie closest to the carbon. So the isopropyl actually was priority 2. And if you notice, there's a lot of scribbling on this one because I got most of the way through grading the entire class before I caught that mistake. And then went back and had to regrade everybody's, so that's why it's a little messy there. So this would be priority 2, and this would be 3. Because it's not just what's the total atomic number of everything over here. It's how do you break the tie as fast as possible. Right, so you can break the tie after 2 carbons if you go to the right, versus it takes you 3 carbons before you can get to a branch if you go towards the left. And then the last one would have been the hydrogen sticking into the board. So this one was an R. A common mistake that people did was, in addition to mixing up the priority, is getting the priority right, but redrawing it and screwing it up when you redrew it. If you redraw it, you have to make sure you keep everything in the same spots, or else if you switch two things, then you're going to get the wrong stereoisomer. Right, so what I would recommend generally is if it's already set up so that your lowest priority is into the board, don't change anything. Assign your priority as it is. If you're going to redraw it exactly the way it is, because you don't need to do any rotating. Lowest priority is already facing away from you, so just leave it. If you have to redraw it, make sure that you redraw it with everything in the right position when you take it and rotate it and move it around. Brad?
Obviously not in that case, since lowest priority was already in the position you wanted. But if you wanted to rotate it, it doesn't matter which one you leave stationary, correct?
Correct. So if all I wanted to do, and what I noticed is that when you tried to redraw it, everybody wanted to put it in the same position as we normally draw tetrahedral carbons, right? With the plane, with the bonds that are in the plane, one going up and one going to the left, or one going to the right. So if you're going to try and do that, take this whole thing and spin it and leave everything where it is so that you would get something that looks like, so that would put your isopropyl group would be going, or I guess it's an isobutyl group, would be going up. And that means that if we rotate it this 60 degrees, that means part with the cyclo group goes down and to the right, and then our chlorine is still coming out towards us over here. Right? If you tried to redraw it so that these two were on that side, you switch the order of 2 and 3 when you go through, or well, 1 and 2, when you go through and do that. And if you switch the order, you just drew the enantiomer, not the original molecule. Right, so anytime you can get away with not moving anything, because number 4 is already into the board, do it. It's going to help you. It's one less place for you to screw up. Not to say that you couldn't do it, but again, high stress situation, avoid places where you could make a mistake if you don't have to do it. The one on the right, and this one, when it came to the priority, I don't think I marked anybody down for getting the priority wrong, because we didn't talk about double bonds, and I didn't realize that. The book talked about them, but basically, if you have a tie going both directions as far as carbons, make a pi bond is usually going to be your tiebreaker. Right? This is not going the same going both directions, because you've got, it takes you two carbons before you get to a pi bond versus 3 carbons before you get to a pi bond. So when in doubt, go with whatever is most complicated. But the number 1 rule is break the tie as fast as possible.
So which would be the higher priority?
So this would be the highest priority, then here, then there. So, and then hydrogen is sticking out.
That's makes sense.
It does. If you don't have anything with different atomic numbers, but it's still definitely different between the two, it's usually you're going to go with whatever has the pi bond first is the higher priority. And there are specialty rules, like if it's an alkyne, if it's a triple bond going one direction, at the same time you reach a double bond going the other direction, the triple bond is going to take precedence. But the rules get the general rule is what's most complicated is going to be the highest priority, assuming you get to it at the same time. And if you get to something more complicated, if we throw a chlorine anywhere in here, that throws everything off. Because now the chlorine matters more than the pi bond. Because a chlorine has more, a higher atomic number than any of the carbons. And so then, do 1, 2, 3, we draw it clockwise, but we're looking at the back of the clock because the hydrogen's sticking out towards us. So if we step through the board and look back this way, no, I did that backwards. S. So it's R, it appears to be R because we're looking at the back of the clock, so it's S.
So if there wasn't a pi bond there, it wouldn't be a chiral center, right?
Exactly.
Okay. Yeah, the ring was like really screwing with, I spent a long time like sitting and like looking at that one because the ring was really throwing me off. But the pi bond makes sense.
And we'll keep working with that because our next chapter, we're going to start with a reaction where chirality matters. Where if you start with the R, if you start with 1 enantiomer, you only get 1 enantiomer for your product. And so we're going to keep practicing visualizing these things in 3D. Brad, did you have a question?
Not a question, just a statement. I was under the same impression that since it was in a ring, I thought everything was the same, so I didn't think that anywhere on the ring was a chiral center.
And again, yeah, so anytime if you don't think there's a chiral center, but you can say, well, this direction around the ring is clearly different than this direction around the ring. Think about if you started out right here and started walking, and all your sp3 carbons are identical McMansions, and you've got, something that looks different. A stoplight when you go one direction around the block versus the other direction around the block. You get to the stoplight faster this way than that way. So it can't be the same in both directions. which tells us that it has to be chiral center, right? So again, we didn't spend that much time doing chirality, and I had just graded your top portion, of which nobody did that well, so I wasn't too harsh, but we'll keep working on that. All right. I threw a little curveball, and then I switched it from transition states to intermediates. That's why I bolded it. Remember, intermediates are stable molecules in between where you start and where you end. But that and that are not intermediates. That's where you start and where you end. That's not a bus stop along the way, that's the end of the road. Right, so the intermediates would have just been 2 and 3.
Yeah, that tripped me up because we're starting from above that point and then getting to it.
So that's part of that is just that's the shape of these these potential energy sources. They're all roughly parabolic. If you can picture a whole bunch of parabolas sort of overlaid on each other. So that shape is there, but if we're saying this is where the reaction starts, then for the purpose of this reaction, that's a reactant and that's a product, and these are the intermediates. Again, I wasn't too harsh on that because if you circled 1, 2, 3, and 4, you still showed me that you were understanding that it was supposed to be the bottom of the potential energy well. It's also harder to see, so that when you publish these, we don't use we don't do a potential energy surface that looks like this because all of this step along the way is not actually calculated. The curved part's not calculated. We just calculate this energy, and this energy. So when you're publishing it, to avoid people thinking that you calculated every energy along the way, we actually just draw it like that. Where all we're seeing calculated are these, they call stationary points, potential minimum or local minimums and maximums. But that's not what they actually look like. It's not like there's this discontinuity here. It really looks something like this, which is why I showed it to you this way, and why I usually, when I'm drawing them by hand on board, I'll usually draw them curved. It's just hard to do it in a way that makes it easy to see with Excel when you're making your figures. And so, yes, I get that can be a little misleading, which is also why it was a pretty minor deduction as well. This one was trickier than I thought it was going to be for you. Fastest has nothing to do with delta G from between the two intermediates. Fastest only has to do with what has the smallest barrier. So fastest, we're looking at 3 to 4. That's a smaller barrier than 2 to 3.
Spooner versus Echo 7, is that the analogy?
Yeah. Spooner has a lower barrier, even though our overall change in altitude going from lake level to Carson is not as big as going from lake level to Sacramento. Going over Echo towards Sacramento, you have to get up higher and then you can go down further, but it's that getting up higher that dictates the rate. Right, so rates are always going to be based on barriers. Equilibrium constants are always going to be based on delta G, which is from one intermediate to the next, or reactant to the next first intermediate. We're going from things at the bottom of potential energy well to the next bottom, the next local minimum. All right, so fastest would have been 3 to 4. Largest equilibrium constant, and largest threw people off too. I was not anticipating that. Largest equilibrium constant means favors the products the most. And favors products the most, now you can just look at delta G. 2 to 3 is a bigger drop than any of the other steps. 1 to 2 is uphill in energy. 2 to 3 is down by 1, 2, 3. I tried to just give you these lines just so you could see, without putting numbers to it, that it was definitely bigger. You go 3 to 4, which is only decreased by 1 unit. right? So largest equilibrium constant would also be 2 to 3. Fastest would be 3 to 4. Most everybody figured out spontaneous. If the overall reaction is downhill in energy, all the way from 1 to 4 is downhill in energy, in free energy, then it's spontaneous. So it has some non-spontaneous steps along the way. Well, namely 1 to 2 is non-spontaneous, but 1 to 4 is spontaneous. Pretty much everybody recognize that rates in general, it doesn't matter. Rates are always uphill in energy, right? So the exact amount that it's uphill in energy doesn't matter. If you increase the temperature, you increase the rate, and vice versa. I took off some small deductions for if you said directly proportional, because directly proportional means linear, and it's not linear. It's also not inversely proportional. It's not proportional at all. They're correlated.
That's the word you were looking for, Riggy. When we were working on it, yeah, we were like proportional, correlated.
Proportional means specifically it's either linear or if it's inversely proportional, that means it's a 1 over x graph.
Actually, as soon as you just said inversely proportional, I was like,
That's what, yeah, because that's the words we were using.
Yes.
Correlated.
Somebody wrote indirectly proportional, and I let that one slide.
Yeah.
But if you said inverse, that means something very specific, and you said directly, that means something very specific. Indirectly proportional, I've never heard of, but it's not wrong.
That's okay. I know where you live.
That makes sense now, thank you.
So all I was looking for is if temperature goes down, K goes down, your rate constant goes down.
The fact that was endothermic matters, right?
For number 2, not for number 1. For rates, because rates, it's always, by definition, a transition state has to be above where you started. So it doesn't really matter if it's endothermic or exothermic or anything else, regardless, delta G is going to be uphill. So all that really matters is how uphill and what the temperature is. And if you're not changing how uphill it is, all that really matters is the temperature. This one was tricky. I'm going to teach you guys a trick for something like this. If you've got a 50-50 shot, make up some numbers. Make up numbers for 2 different cases. And I recognize you didn't have a calculator with you necessarily, but at the same time, if you make up numbers that are easy to do in your head, you should be able to get to something where you can plug it in and see. Okay, because if we just look at it in our normal sense here, we say, okay, well, delta G is equal to delta H minus T delta S. If delta H is positive and delta S, so T is always going to be positive and delta S is also positive, this term favors being spontaneous, right? And when your temperature decreases, the term that favors being spontaneous gets smaller. And so that means as the temperature drops, it gets less spontaneous, which also means that your equilibrium constant should favor the reactants more and more as your temperature drops. Right, so K, in this case, this is where we need to think endothermic and delta S in order to see this. As temperature drops, it gets less spontaneous. Therefore, equilibrium constant should get smaller. And if you have the equation in your head, again, it's a 50-50 shot. If I'm asking a point blank like this, it shouldn't even matter what numbers you pick, right? I'm asking a point blank question with no numbers qualitatively. So pick any numbers that are convenient. And say, okay, well, I'm gonna say that delta H is 1,000, is plus 1,000. And I'm gonna say delta S is, so it doesn't really matter, but delta S is usually smaller than delta H. So I'm gonna say it's plus 50. But you can pick any number you wanted, doesn't make a difference.
Is endothermic positive or negative values?
Positive, because endothermic means you're taking energy away from the surroundings and it's going into the chemicals.
Yeah, that's, so I did that backwards.
And if you just make up two temperatures, if you just leave these the same and make up two temperatures and see what the difference is for delta G, you say, okay, I'm going to look at temperature equals 50 Kelvin and temperature equals 100 Kelvin. At 50 Kelvin, delta G is going to be 1,000 minus 50 times 50, right? So 2,500. So plus 1,000 minus 50 Kelvin times plus 50 Kelvin, or plus 50 joules per mole Kelvin. But if we're just trying to go fast and you're doing this in your head, that's not that critical. Keep your units the same. So we get delta G for this case would be negative 1,500. If we do the same thing with the plug 100 in for temperature, you get delta G equals, get 100 times, so you get 5,000 instead of 2,500. So delta G overall winds up being negative 4,000. So because this can get tricky, sometimes, especially in a test situation, you're not sure what to do, just make up numbers. Here's my high temperature case, here's my low temperature case. When temperature dropped, if you started there and your temperature dropped, delta G got less negative. And if you follow that through for our equation too, we can see, so without even having a calculator, you can still plug it in and say, okay, well, e to the minus negative 1,500 over r times 50. Versus on this side, k equals e to the negative minus 4,000 over r times 100. That, if you can't see the difference in the numbers in your head, you can do a little simplifying. This is literally when I got 2/3 of the way through grading these last night, and somebody wrote an explanation that was backwards. It was convincing enough. They said, maybe I do have it wrong, and I just did this on my whiteboard and behind my desk. And just without a calculator, you can still wind up with that being, so now we have 4,000 over 100, which is just 40, right? And the two negatives cancel out, so 40 over r. And on this side, you get E equals 1,500 over 50 is 30 over r. And negative and a negative again. So at the high temperature, you get E to the 40 over r versus low temperature, E to the 30 over r. Now we're comparing apples to apples. We're actually talking, now we've removed all of the layers of how complicated this can get, right? High temperature, K is bigger than low temperature. And so if you get yourself in a situation, because this is a really complicated thing to work yourself through, especially when you've got to think about delta G before you even get to this weird function. So when in doubt, especially if you have time, give it your best go. If you're trying to go fast, make sure you've answered everything at least a little bit. And then come back to like, okay, I'm still not sure about how I answered this. Pick two numbers and give it a go. And see if you can get two numbers that show you concretely what works and doesn't work.
So if it's e to the exponent, positive exponent, we don't put 1 over whatever that is, like it's just,
This is our, exactly, this is
okay. So the 40 would yield a larger K than the 30.
correct.
Okay,
And that's what matters with these negative signs, is getting to cancel out.
okay, okay,
And if you happen to pick numbers where you wind up with one of them negative and one of them positive, that still works, because if this was negative and that one was positive, you're gonna, if it's a negative exponent, you're gonna get something that's less than 1. If it's a positive exponent, it will always be greater than 1.
okay.
So it still works, even if you wind up with a weird case where you've got one negative and one positive.
So what's the simplest verbiage you can put that answer in?
I would not even get into K.
Yeah.
I would do it just qualitatively, the way we started, delta G equals delta H
Right.
minus T delta S, and I'd say, okay, if that's positive, it favors non-spontaneous.
Okay.
Which another way of saying that is favors K being less than 1. Over here, we have a term that favors K being greater than 1, or favors being spontaneous. When your temperature drops, the favorable term gets smaller. So overall, the overall reaction gets less favorable in the terms of spontaneity. It gets less spontaneous when the temperature drops. And so being one step further removed, you say, okay, less spontaneous also means K is smaller because it favors the reactants more than the products. And so the simplest, you could just write it. You wrote this and then you said, when T goes down, delta G goes up. Therefore, K gets smaller. Be the fewest number of words that you could say there. That just pick a number and try it out approach also works on math tests sometimes if you're trying to do a proof, or if you're trying to do an integral or something like that, and you're trying to, your final answer is supposed to be the indefinite form. You're not sure, like, pick something that you know you can do in your head, that you know you can get right, and just plug a number in and see if it gives you the number that you think it should. Right, so it's, it's a really powerful way to check your answer if you have the time to do it. But it does take time, and you have to be able to pick numbers that make sense. All right, we're past when we normally take a break, but we're also almost done going through the test. So let's just keep going for these last two. I'm not going to spend any time on 9 because everybody got close to full credit on number 9, with the exception. Actually, not really with any exceptions. I actually gave 1 extra credit point if you actually label this as being resonance structures. This step was the proton transfer. These are all just resonance structures. So if you labeled them as being resonance structures, you got an extra point. But I didn't, if you labeled this whole thing as a proton transfer, with including this part, I didn't get too busy, because it was a proton transfer just right over there.
What is B?
B is a rearrangement. Right, it's a weird looking one because it's not a hydrogen moving, it's a methyl group moving, but it's still, our definition of rearrangement was a sigma bond moves to make a more stable intermediate. It's a methyl shift, as opposed to normally we'd call it a hydride shift, because it's a hydrogen with a pair of electrons moving over, which is a hydride, not just a hydrogen. And this is a methyl shift, but it's the same, it looks the same. If I drew an H right here, now it's a hydrogen shift, a hydride shift. Right, so it's the same logic. You've got a carbocation, you can have a small group like a methyl or a hydrogen move over to make a more stable carbocation. And then these ones. We didn't do so hot on these. That's okay, so I sprung it on you at the last minute. Key thing that I will remind everybody of is our arrows always have to be from electrons towards a nucleus. Right, so even if you have no idea what you're doing, pick a pair of electrons and draw an arrow towards a positive charge. Even if it doesn't get where you're going next, like, okay, if I totally got this wrong, the right answer looked like this for the first step. It's a proton transfer. Lone pair on the oxygen grabs a proton, and then the oxygen had the proton keeps the electrons. If I really got this wrong, I could still get more partial credit and maybe have a shot at being right if I did like that. Take a pair of electrons and draw an arrow from that pair of electrons towards a positive charge. If this is actually what happened, we would get something weird like a peroxide bond forming, something that looked like, and then to the rest of the molecule there. And, we'd get something weird that looked like that. Now we have an oxygen with 4 bonds. Really not all that stable, but at the very least, the arrow that I drew followed our most basic rules, which is show an electron moving towards a positive charge. Right? As weird as this is, and as much as this doesn't match with what the next step was, this is going to get you more partial credit because you still followed our rules for mechanisms. And in this case, for problems like this, where I give you have the intermediates the whole way through, and all you have to do is show the electron movement, look at what you have before and after and look at what's different. And then just draw the arrows to make that happen. We have the same molecule before and after, except we have an extra hydrogen on it now. We have 1 fewer lone pair on the oxygen now. Therefore, a lone pair had to have grabbed a proton from something. And so, when you know what the steps are, drawing the arrows should always make sense, even if it's hard to come up with on the fly. The first thing that you guys are going to do with mechanisms when on a test is you're going to memorize mechanisms, because that's easier than coming up with it on the fly. And then as soon as you start seeing the patterns in the mechanisms, you're going to start trying to do your mechanisms on the fly on the test without having the intermediates drawn. And you're going to wind up taking a left turn somewhere and coming up with something totally wrong. And that's normal. My lowest grade on a chemistry test ever was when I thought I got how to draw mechanisms from on the fly. So I went into my midterm for my OChem class and started trying, and I kind of nothing that was anything close to the right answer. But it's still the same rules. You just have to know kind of where you're trying to go to kind of shepherd yourself, make sure you didn't go the wrong direction. If you know you're trying to go from Sacramento to Denver, you probably don't want to get on any freeways that say west, right? It's really easy when you're drawing these mechanisms to accidentally get on a freeway going west when you're in the middle of Utah and wind up somewhere totally different. You wind up in Twin Falls, Idaho. Congratulations. That's a lot like Denver, right? All right, so we will continue practicing with these. Like I said, overall, I knew that was going to be the push question, that everybody was going to struggle with that one because we didn't practice it as much, and it's the hardest thing we've covered so far. So don't stress about that one too much, or anybody's overall grade. Everybody's still in pretty good shape in this class. So let's take a quick break. We'll come back and we'll cover a couple minutes of new material. Let's come back to 25 after. And then we will do a couple minutes of new stuff.
Couple quick questions about this setting up this drinking glass.
Yeah, I got Rachel started on grabbing some of this stuff.
Oh, cool. I don't remember using like an acid thing on the crystals.
We did a little bit. We kind of, basically what you have to do is make sure that whatever is still left in there has fully reacted as much as it's going to. So it's,
So that it's going to slowly get out.
yeah, but it just, like, it's just gonna be a couple drops each, so like one bottle with a dropper attached to it, that they can use.
Like a little.
And so whatever's already mixed up, but let's go look and see what's already made.
Right. And then, yeah, let's move up the track.
He makes it look so easy.
What's that?
I said he makes it look so easy.
Oh, yeah, right? Sometimes before a test, I just want to hang out around it. Usually I don't. Right? It looks like it's going to be pretty easy on it. Hopefully. Yeah, it looks like it's going to be extraction and analysis of essential oils. There's some flow, there's some lemon peel or something.
So basically, just spill it, yeah.
Yep. Be careful.
I didn't take this class for biochem before the MCAT, and I feel like if I would have had this knowledge, I would have scored probably at least like 5-10 points higher.
So that's.
That's
Those 5 or 10 points, that's significant.
It would like bump me up from like the average to like above average. So
Yeah.
I do think I'd do better on it if I took it. This is the process. If you take the test, it's an 8-hour test.
Yeah.
You go to a testing center, you take it, and then you have to wait 6 weeks to get your score back. It's It's brutal. It's brutal.
This is good.
And not waiting, because like you walk out of there feeling like you get totally wrecked. And then you have to wait 6 weeks knowing like just how badly you got wrecked, or you surprised yourself. It's bad. I really don't want to do that
And
again.
what are the other options outside of UNR? Are you using Sac State or Davis or anything that way?
So the UC schools are like super competitive. Like if I don't get into UNR, I don't have a chance in hell of getting into the California school. And I'm not a California resident.
Oh,
So I'm a Nevada resident. So UNLV would probably be, but I don't really move.
that's what it's at.
Yeah.
Viva Las Vegas. Uh-oh. I heard that.
Sorry,
I heard.
apologize for leading you astray and,
No, hey, it's not your fault. We were bouncing off together and we both couldn't come up with
both
the
went
right
into the
word.
wrong direction with that.
We're doing a demo with hydrates and how hydrates change color.
That's a pretty color.
And if you take
Oh, nice.
copper chloride and it's dissolve it in water, you get a nice blue color. But if you dissolve it in methanol, it turns really bright green. And then plus side, it then becomes flammable, and you can do this. And yeah,
That's really cool.
it is. You're not supposed to do it like this anymore without being put in your head, but you have the proper protective gear. But
We won't see it.
you guys are going to stay all the way back over there, and I'm not going to sue the school. So
There's
it's
some,
not over this anymore.
there's some power in that, see that?
That's cool.
Yeah,
We have masks on this.
it's yeah, for sure. All right, so let's talk about substitution reactions a bit. A little bit.
I don't know
Brad.
where that would come from.
What was just burning? Like,
Copper, so that was, the methanol was burning, but when you heat it, and it started that really normal blue color, which is normal methanol flame. But as the copper got hot enough, the copper wasn't burning, but it got hot enough to excite the electrons to a higher energy level, and then when they fall back down, they give off, so we're exciting it with heat, and then when it falls back down, it gives off a specific wavelength of light.
yeah.
So the methanol was all that was burning. You don't actually need methanol. The boring way to do this is to take a solution in water, put a little tiny drop on a wider loop, and hold it over a Bunsen burner. And as the water burns off, or evaporates off, you get a very brief second of green colored flame. But it's not nearly as fun. All right,
So,
so go ahead.
those electrons were being excited, the ones in the copper?
The copper. And so if you do this with a different ion, if you do it with a different metal ion, you get a different color. If you do it with sodium, you get the yellow that we think of as being normal fire color. If you do it with, let's see, potassium, you get like this faint purpley lilac color. It's really hard to see, but when you turn lights on, you can see it pretty well. Chromium, depends on what the oxidation state is. You can get lots of different colors of chromium. What are some of the other ones? Strontium, it's like a really, really deep red color, almost like a purplish red.
Would iron and magnesium be ones too?
Magnesium just burns pure white. And so you can actually see it, but it's hard to see a white flame against a blue flame from the methanol. But there are some common colors. Most of the common colors that you see in fireworks, you can do. The reason the fireworks have those colors is because it's different metal ions mixed in with something that burns and gets to a high temperature.
Barium does a nice one, I can't think of it.
Barium might be green as well. It might be another green. Blue is hard to do because copper looks blue when it's oxidized, but when you get it at high temperatures, it actually gives off a green color, not blue. And that's why you don't see very many true blue fireworks. You see purple fireworks and you see green fireworks, but you don't see blue very often because there's not that much that's not really, really toxic to give you that blue color.
Plus, if I remember correctly, blue is a higher frequency.
It's higher energy, so to get it there, to get it up to blue without going too far and winding up in ultraviolet is hard. Although we can get purple, so it's something about the way the orbitals work. Yeah, numerically, it's hard to find a good fit for blue. Right.
So since Hannah and I know we got the time thing going on here, since she and I aced the quiz over the weekend, do we get extra credit for going above and beyond?
You'll see it again next week. We're just off by a week because of the whole,
Thank
the
goodness,
color
I
fire
didn't understand any of
thing.
that. Okay.
But actually, it might not even be this week since we're not gonna have lecture on Thursday. So,
Oh, we don't have lecture on Thursday?
so it's one of those things, we don't have lecture on Thursday for Veterans Day.
Oh.
So we'll go through this. It's still worth spending, even if it's just 20 minutes on it, because it's one of those things, when you hear it twice, it'll make a lot more sense. So we're gonna talk about reactions of alkyl halides. And alkyl halides means specifically we're going to be dealing with halogens that are attached to an sp3 carbon. So not vinyl halides and not aryl halides. And remember, vinyl halides, that's PVC, polyvinyl chloride, is what reacts to give us PVC. These react differently because of the pi bonds and all the resonance that can happen when you have a lone pair adjacent to a pi bond. So, but alkyl halides are actually one of the simplest classes of molecules, and we already all know how to name them because we just use those chloro-bromo prefixes, right? There's basically only two reactions that they go through. And so this is why this is a good first step into reactions, because there's not a whole big range of things we have to worry about. Alkyl halides basically will only go through either a substitution reaction, where a nucleophile comes in and basically pushes off the halide and replaces it. So substitution, aptly named, all we're doing is we're substituting a different nucleophile for our halide. And then the other reaction is an elimination reaction. In an elimination reaction, your halide is going to leave still, but instead of having another nucleophile come in and replace it, we make a pi bond instead. So elimination reactions are always going to give you an alkene. A substitution reaction, you're going to get almost the same molecule, but with a new nucleophile attached. So we're going to start with substitutions, and then we'll talk about eliminations, and then we'll talk about how they actually both happen at the same time. Brad?
That be our lot nucleotides?
You did a substitution of bromobutane, right? And you had it react with, we did it under acid catalyzed conditions, not base catalyzed conditions, but it was a similar reaction. And what did the reaction give you at the end? We made bromobutane, we started, so we actually did a reverse of the substitution we're going to see first, where we replace an OH group with a bromine. In this case, we're actually going to replace the bromine, or whatever halogen you have, chlorine in this case, with an OH group. So it's undoing the same reaction that you did. It's still considered a substitution reaction though. All right, so let me make sure we don't run out of battery here. So the product here is, of any substitution reaction, is you're going to have a leaving group that leaves, and you're just going to replace it with whatever your nucleophile is. So what's a nucleophile out of this? Or maybe a little review. What's a nucleophile in general?
Negatively charged.
It's negatively charged, it's attracted to a positive charge. So if I blow up our 2-chloropropane and look at where the chlorine's attached, where is the positive charge, or a partial positive charge here?
On the chlorine.
On the carbon attached to chlorine.
The chlorine is more electronegative, right?
Yeah, but I was thinking of reference when I said it. I guess I shouldn't have done it.
No, you're good. So we have a partial negative here, a partial positive here. what about this is going to be attracted to any part of our molecule? The OH, the hydroxide, has a full negative charge, right?
Yeah.
That's going to be attracted to the partial positive, but we don't have room for it. Carbon's already sp3, it already has a full valence, so to make room for it, the chlorine has to get booted. So our net result of this reaction is we're just going to wind up making propane with an OH attached where the chlorine was. And chloride. Right, because you started with something with a negative charge, you kicked off the chlorine, and it took its electrons with it to make room for the hydroxide. So you're still going to have chloride around. And this, but in general, we worry less about balancing reactions in OChem than we did in Gen Chem, which is why on the practice test and on the mechanisms part, you would just frequently see, here's a new thing that's coming in, or we lost the water and it just disappears, never to be seen again. That's really common in organic mechanisms because we care mostly about the organic compounds, not whatever else is around. I should say we care less about whatever else is around. Brett?
I'm just curious as to why the chlorine would get booted off. Is it because it's a full negative charge? Do you see what I'm saying? Like, the forces at play here, is it because it's a full negative versus a partial negative?
So what you're really asking is, does this equilibrium reaction favor making the products, or does it favor the reactants?
Yeah, pretty much.
I'm glad you asked that.
A question for that, how's well presented?
Basically, we have a list it's related to pKa values, which I know we're all probably looking forward to not thinking about pKa values again. But effectively, whatever is the strongest acid, the conjugate base of that acid, it's a strong acid because the conjugate base is so stable on its own. Which we can also continue that logic. Say, if the conjugate base is really stable on its own, it also means it's a good leaving group. So because hydroxide is less stable on its own than chloride is, this reaction will favor making the product, favor this side of the equilibrium. Right, and so we just have a table that has a list of, okay, they're not all this detailed, but if you have a list of pKa values, whatever has a lower pKa means it's a stronger acid, right? And a stronger acid means the conjugate base is a better leaving group. Right, so pKa winds up being really, really helpful in OChem for estimating whether or not our reaction favors products or reactants, because two of our 4 steps that we learned for mechanisms were nucleophile attacks and leaving group leaves, right? Well, what else do we notice about all these leaving groups? They're all negative, which means they're also all nucleophiles. So every leaving group on this page is also a nucleophile. The better it is at being a leaving group, the worse it is at being a nucleophile. Right? Because if it's a good leaving group, it's stable on its own. If it's a bad leaving group, that means it's going to go out and find something to bond with, find a positive charge, and attack it. Right? So all we want to know, if we want to know whether this reaction favors products or reactants, and remember I drew it backwards, this was our reactants initially. We want to know whether it favors the chloropropane versus the propanol, isopropyl alcohol. We look at this and say, okay, well, chlorine's all the way up here, pKa of -7. Hydroxide's all the way down here, pKa of about 16. So hydroxide is a much worse leaving group which means it's a much better nucleophile. If we started here, this is what you guys did in lab the other day, is you started here, and even though hydroxide's a bad leaving group, we were able to make some of the product using bromine as a nucleophile. Mostly because we didn't actually leave it as hydroxide. We actually turned it into hydronium by adding acid, right? So instead of having OH as our leaving group to make hydroxide, we had water as our leaving group. That's a much better leaving group than hydroxide. It's way higher up on this list. pK of -2. So we're still going to have an equilibrium reaction happening because we're still trying to use a nucleophile that's not as strong as our leaving group is. So there are other things we can do. Remind me of that procedure. Do you guys use bromine or bromide?
Sodium bromide.
Sodium bromide. So, but effectively, if you can do something like, if we look at what the balanced reaction would be for that, so let me adjust this. So we have an equilibrium reaction happening where we had those reacting. It's our bromide coming in, pushing off here, right, to make and if I tell you this is everything we're going to be dealing with from basically from here on out, it's going to be an equilibrium reaction, right? We've now everything can happen in both directions if we mess with the conditions. What can we do to increase how much product we make here?
Temperature,
Temperature might be a factor. Why?
because it's favored towards reactants, increasing the temperature will push it towards products.
Increasing the temperature. If equilibrium, if it's endothermic, then adding more temperature on the reactant side is like adding more reactant. And Le Chatelier say that makes more product then.
We can also remove water.
We could also remove water. If we take away one of our reactants, or products rather, then we can't get to equilibrium without making more product, right? So heat actually does two different things here. One, the most significant is actually that we can boil off the water. If we're removing water, that actually is going to favor making more product. Plus, it'll actually change, increasing the temperature. We can predict this. We're adding enough heat to turn this into a gas. Versus over here, we had aqueous and a liquid. We had enough heat that we're actually turning this into a gas. Which side is favored by entropy?
Right.
The right side. So even if it's endothermic, we can predict that adding temperature is going to make it more spontaneous because we're going to start making the side that has more entropy at higher temperatures. So I told you that delta G was going to keep coming back because basically everything we do in synthesis is how do I tweak this equilibrium reaction to get me more product and less of something else. Right, so we're typically going to present it for this chapter as though these are our best leaving groups, are the halides. So these are really good tools for synthesis as well, because if you can put a chlorine where you want to put anything else, all you have to do is have a good nucleophile come in and displace the chlorine to make something else. And it turns out one of our first reactions when we talk about alkanes is going to be how do we put chlorine where we want it? And once you put chlorine where you want it, you can make anything. All right, and look at that. We happen to have that same exact example we were just talking about right here. So in this case, the bromide is the better leaving group than hydroxide by a long shot. Remember, our pKa is all the way down here, 15.7. And it's not a direct rule, it's, you guys remember how to do Hess's law, where we could add up different reactions and cancel out things that were both a product and a reactant to get some new reaction? Did that for energies, and we did that for equilibrium constants too, where you could combine reactions. This is the equilibrium constant for this acting as an acid with water, but you can still use the difference in these pKa's to talk about how stable they are as leaving groups, because you can wind up with the reactions adding up and canceling things out. So we can actually look at this and say, okay, well, difference in pKa values, let's just call that 16 to -9. Remember, the pH scale is logarithmic, right?
Base 10, yeah.
Base 10. So -9 to 16 is a difference of 25 times, right? So 10 to the 25 times better leaving group. Bromine is a better leaving group by a factor of 10 to the 25, which means you can expect that K is going to be something like 10 to the 25. So an absurdly large number. But if we protonate it to go from being hydroxide, let me go back to the other chart here that has water on it, from -9 to -2 is only 10 to the 7. So still favors the bromine being the leaving group by a factor of 10 to the 7, but 10 to the 7 is a lot different than 10 to the 25. Right? 10 million versus a mole versus 100 moles. What if we protonate the OH and we're using fluoride as our leaving group instead of bromide? Now which one's a better leaving group? So -2 versus fluorine's all the way down here. Fluorine's not a strong acid, right? It's the only one of our halogens that doesn't make a strong acid. It's got a pKa of 3. So this actually favors the water being a better leaving group by a factor of 10 to the 5. Right, so by tweaking conditions and tweaking what our leaving group is, we can change a lot of things about the equilibrium. And so sometimes it's making small steps along the way. Sometimes what you have to do is, okay, I'm going to start by replacing my iodine with a fluorine, and then I'm going to change, and then I'm going to do it under acidic conditions to make the oxygen a better leaving group. And then I can go back and then replace the fluorine with something else after I use the fluorine as a nucleophile. I can come back, and so you wind up having to do multiple steps sometimes to get one overall reaction that would have a hugely negative or hugely positive K value. You can tweak that by going in small steps around the outside, basically. All right. Last thing we're going to go over today is that there are 2 possible ways this reaction can happen. This is a pretty simple mechanism, all things considered, right? It's only 2 arrows to get us all the way from our reactants to our products, right? So if there's only 2 arrows, at its most basic, there are really only 2 ways we can arrange them. Either they're both going to happen at the same time, or, finish my thought for me. Stepwise, in more than one step so that it goes 1 arrow at a time. All right, so I'm going to switch this now so that we're looking at the halogen being the leaving group, because that's what this whole chapter is focused on. So we can have both arrows at the same time, or we can have one then the other. Which one has to go first? We're going to do one then the other.
Leaving group on
Can't have the carbon with 10 bonds, right? So you can't have the nucleophile attack before the leaving group leaves. It can happen at the same time, or your leaving group can leave first. Right, so a concerted mechanism all at once means you only have 1 reaction arrow. You have 2 mechanism arrows. Nucleophile attacks, leaving group leaves, just like we have on the board. if it's stepwise, stepwise means in more than one step, or one step at a time, your leaving group leaves first, and that's going to give us an intermediate. So if it happens in 2 steps, we have to have an intermediate. And what is the intermediate going to look like? The leaving group leaves. When a leaving group leaves, the electrons always go with the side that's more electronegative, which means if a leaving group leaves, where do the electrons go? With the leaving group or stay on the carbon?
The leaving group.
With the leaving group, right? So what we're left with is a carbocation. A carbon that is now missing a pair of electrons. And a lot of times when we do this, when we draw this, so we don't have to keep drawing the bromine, you'll just see it written like this. This just means the bromide's gone. Hence the minus sign. There's a minus sign meaning we lose a bromine. And now we have an empty spot on our carbon, an empty valence spot in the valence for a nucleophile to come in and attach. Right, so same 2 steps, they're either happening both at the same time or in 2 steps. It's the same 2 arrows. Leaving group leaves, nucleophile attacks. Which is why this brand of substitution is called a nucleophilic substitution. You need a nucleophile for this to happen. It's always leaving group leaves, nucleophile attacks. All right, we'll end there. We will do something of a quiz this weekend because otherwise it's going to be a whole 7 days before you think about OChem again. I'll have it go open on Thursday, and it'll just be something simple like which is a better leaving group. Maybe a couple review, but maybe some R and some S practice since we could use that. But it's the only new stuff that's going to be on leaving groups.
I still have the Gen Chem textbook, the atmospheric one.
Yeah.
What chapter is the good review for pKa?
So that where you're talking about, where it's talking about weak acids and weak bases. I don't remember what number that is, but it would have been the 2nd equilibrium chapter. Probably like 14, chapter 14 maybe. I haven't taught 102 in a long time. Somewhere in equilibrium, right? It's in the table in the Gen Chem book is not going to have all the same stuff because it's more concerned with like nitrate and sulfate and things that we don't care about anymore, or we care less about. I should say.
What is it more?
Yeah, definitely 102, and then because you guys didn't get to rates until 103, right?
Yeah.
So maybe it's earlier than 14. That might have been when we did rates first. It might be like chapter 11.